All right, welcome to Let's Get to the Marks. This is the A-level chemistry walkthrough for paper 1, 2023 for the AQA syllabus. This is the organic and physical chemistry paper taken on the Monday, the 12th of June, 2023. There's 10 questions. It's a 2-hour exam. I suggest you pause the video at the start of each question and then have a go. Okay, question 1. The question is about complexes of the transition metal chromium. State the meaning of the term transition metal complex. 1 mark. So here we got to think, what is a transition metal? And essentially it's a meshel. It's a metal atom or ion. That means you can say either one in your definition, surrounded by ligands or ligands. Ligands, of course, are species that can donate a pair of electrons to a central metal atom, like a transition metal. Okay, let's look at question 1.2. The electron pair repulsion theory can be used to predict the shape of a pF3 molecule. Draw the shape of a pF3 molecule, include any lone pairs of electrons that influence the shape, and you need to name the shape. Okay, so we need to go through. I'm going to go through how you work out the shape. So phosphorus is an element you'll find in group 5 of your periodic table, and it has 5 electrons around the central atom. If you combine that with the little 3 next to the F, then it's got 3 electrons that have been given to it from those 3 fluorine atoms. So there's a total of 8 electrons around the central phosphorus atom. So how many pairs of electrons does that make? Well, that makes 4 pairs, because if you do 8 divided by 2, you're going to get 4. So there's 4 pairs of electrons floating around the central atom. Now we need to work out how many of those pairs are in bonds, tied into bonds, and how many of those pairs are lone pairs. Well, think about it. The fluorine is donating 3 electrons, which will be bonded, shared with 3 electrons from the phosphorus. So 6 of the electrons are paired, and there's 2 electrons floating around. So we have 1 lone pair. A total of, how do you work out the number of lone pairs? Well, you do the bonded pairs. You do total pairs, which is 4 minus the bonded pairs. So we've got 4 total pairs of electrons minus the 3 bonded pairs of electrons gives us 1 lone pair. So essentially there are 4 pairs of electrons around the phosphorus, and 1 of them is a lone pair. Now, how does that help us out with the shape? Here's where you've got to have done your revision, because you should know that if there are 4 pairs of electrons, there are 3 possibilities, and that is a tetrahedral, which is 4 pairs with no lone pairs, pyramidal, and that is 4 pairs and 1 of them is lone. And then there is bent or non-linear, like water, which is 4 pairs of electrons around the central atom, but 2 are lone pairs. Now, as we only have 1 lone pair here, we're going to draw a pyramidal structure. So you show the lone pair on top. You don't have to do the little cloud, but you do have to put the 2 dots. If you don't do the cloud, I've put both. And then you draw the 3 fluorine atoms forming the pyramid at the bottom. So that's the correct shape, and the name is pyramidal. Lovely. Okay, 1.3, suggest why the oxidation state of chromium is 0 in the following complex. So we're going to get into that. Oh yeah, and just out of interest, the bond angle in the one above in PF3 is going to be 107, because it's 109.5 in tetrahedral, and then you minus 2.5 with each of, as you get a lone pair with each one. So it goes from 109.5 to 107, then 104.5. Right. So now for this 1.3, we want to suggest why the oxidation state of chromium is 0 in the following molecule, which is CrPF3 6. And what we have to realize here is that PF3 is not charged. That means it doesn't have a positive charge or a negative charge. So overall, because the ligands aren't charged, there is no overall charge on this complex. And that's the answer to 1.3. Now, if you're finding this walkthrough useful, don't forget to share, like, and subscribe. The more likes you give me, the more time I can donate to making more of these walkthroughs. Okay, cool. And also leave any comments with things you think would improve it. Sometimes I think I could have some music on in the background or something else. Okay, 1.4, deduce, that means work out, by the way, the oxidation state of chromium in CrNH3. So that's an ammonia molecule as our ligand here. So we've got NH3 with 4 of them. And then we've got Cl2 and then Cl outside the brackets. So we want to deduce the charge on the chromium. Well, ammonia has no charge as a ligand, so that we're not going to take that into account. But what do we know about chlorine? What do we say the oxidation state of chlorine is? Well, chlorine you'll find is a halogen in group 7, and they have an oxidation state of -1 that you should know off by heart by now. So the fact that we've got 3 chlorines altogether, we have a total oxidation, a negative oxidation state of -3. And as there's no overall charge in this transition metal complex, that tells us that the chromium must be +3 because it's cancelling out the -3 charge. So overall, there's no charge in this complex, and that's why. We don't need to worry about things like ligand, ammonia when it's a ligand, or water, or ligand, however you want to say it. They don't have a charge. Okay, cool. So the oxidation state of the chromium is +3. Name the type of bond between nitrogen and hydrogen in ammonia. So when we think of the ammonia molecule, the typical bond we think of is the one that the ammonia forms with hydrogen to form an ammonium ion, the dative covalent bond. I've just drawn that here with the 2 dots and the arrow going to the H. But this is a little bit of a tricky question. I imagine some people will make the mistake and say dative covalent here. Of course, they're not asking about that bond. They're asking about this one I've circled in green, and that is just a normal covalent bond. Remember, it's a non-metal to non-metal. That's going to be covalent. Nitrogen and hydrogen are both non-metals, so it's a covalent bond. Okay. The dative covalent is when it donates a pair of electrons. Okay, let's go. Make sure you press pause on the video before you try to answer a question. Okay, let's get into 1.6. The compound CrNH3 brackets 4 Cl2 transition metal brackets chlorine contains a complex ion that shows isomerism. Draw the 2 isomers of the complex ion and state the type of isomerism shown. So we've got 2 isomers to draw here. And they are just going to be like this. And this is just one of those ones, again, you have to learn. Okay, so we are doing, it's kind of like cis and trans, or EZ. Now, you'd normally only find this type of isomerism when you have a double bond. In alkenes, you can always think of there's no rotation around the double bond. But in complex ions, we also get cis and trans. Think cisplatin that you have to know about. What we have here is this one over here, where we have all the ammonia molecules on one side and the chlorines on the other. Or actually they're on both sides. And then we have this one here where you've got 1 chlorine up above and 1 chlorine down below, and it's not on the same plane now as the ammonia molecules. Now notice I've put a positive charge outside the brackets. Why has it suddenly become positive? Well, the original complex ion doesn't have the chlorine that's outside the brackets. So there's only 2 chlorines in this because you're only drawing the ones inside the brackets. And if you think of the original, it has a chlorine outside. So we have a cis isomer and we have a trans isomer. So it's cis trans, or you can call it EZ. All right, folks, let's get on to 1.7. Complete the equation to show the formation of one complex ion that contains chromium in its +3 oxidation state. So we've got Cl3 plus 5 H2O. So what we want to do is draw a complex ion that contains all of these and has chromium in a +3 oxidation state. Well, we know that chromium is going to be in a +3 state if I have 3 chlorines about it, and that's because the chloride ions are each in a -1 state. So we're just going to write Cr, H2O in brackets 5, Cl inside the brackets, and then it's overall got a 2+ charge. Just like that. Now we only got 6 ligands altogether. So the trick here, you could also write the 2 chloride ions off the side. The trick here is you might be thinking, well, hold on, why can't I include the other chlorine atoms inside the transition metal? Remember, chromium, for instance, will only have 6 ligands around it. So what we've got here is all 5 waters and a chlorine, and the other 2 chlorines come off the side. So overall, this is a +2 charge for the complex ion, but the chromium itself has a +3 charge. Figure 1 shows a cell used to measure the standard electrode potential for the half cell. We've got Mg2 plus 2 electrons goes to magnesium solid. 2.1. State the purpose of the salt bridge. That's this little tube here connecting the 2 beakers. What's the purpose of it? Part 2 of 2.1. Identify an ionic compound that could be used in the salt bridge. So, the purpose of the salt bridge is to complete the circuit so that we have a complete circuit. If you remove the salt bridge, the voltmeter will show no reading, and so the circuit will not be complete. Best not to put so electrons can flow here, because it's not actually electrons that go through the salt bridge, it's ions. So it's best just to say to complete the circuit. Now for the second part of this question, it wants us to name a compound that can be used inside the salt bridge. And really we want to pick an ionic compound or a solution where the metal is more reactive than the one in the half cell. So for instance, if I used copper nitrate, that would be a problem because the magnesium would start displacing the copper and forming magnesium nitrate, and that's not what we want. The salt bridge, we don't want it to get involved in any chemical reactions. So pick an electrolyte to go in the salt bridge or a chemical in the salt bridge that is not going to get involved because it's more reactive. It's going to hang on to its nitrate and not bother reacting with either the electrolyte or the electrode. So we don't want, if I use potassium nitrate and sodium nitrate, sodium and potassium are both more reactive than magnesium, so they're not going to react with the magnesium electrode or the magnesium chloride electrolyte. Okay. Right. There we go. And that's going to get you 2 marks, one for saying complete the circuit and one for suggesting a suitable compound for the salt bridge. Now let's look at 2.2. State, if at all, the electromotive force of this cell, how they'll change if the surface area of the platinum electrode is increased. Right, the only conditions you need to memorize that change the EMF is if you change the type of electrode and the substance in the electrolyte. Surface area has no effect on the electromotive force. So the only factors that affect electromotive force are when you change a condition to do with the electrode or the electrolyte. Okay, let's look at 2.3. Water is added to the beaker containing the magnesium chloride solution. Right, we're messing around with the electrolyte now, so this is going to change the electromotive force. What is the effect on the magnitude of the electromotive force if you add water and dilute the magnesium 2+ ions? Well, I use Le Chatelier's principle here. You're decreasing the concentration of magnesium 2+ ions by adding water. You're diluting that aqueous solution, right? That's going to cause the reaction above here, which is shifting to the right, to shift to the left. It's going to cause more magnesium atoms to break down from the electrode in order to increase the concentration of magnesium ions. So if you dilute the electrolyte, you will always, if you dilute the solution of magnesium ions, you are going to increase the EMF. And that goes for any metal ion in a half cell. If you dilute it, you will increase the EMF because by Le Chatelier's principle, it's going to create more ions. Okay. 2.4, the voltmeter shown in figure 1 is replaced by a bulb. But the question says, give an equation for the overall reaction that occurs when the cell is operating. Well, we've got magnesium chloride, and we end up, we've also got hydrogen and hydrochloric acid. So we have a reaction here, which is magnesium plus hydrochloric acid. What's that going to form? It's going to form magnesium chloride and hydrogen gas. It's just metal and acid. Makes magnesium chloride and hydrogen gas. Cool. Right. Let's move on to the next question. So, question 3. This is about the period 3 elements and their oxides. Give an equation for the reaction between phosphorus and excess and an excess of oxygen. Right. What's unusual here is that phosphorus is a tetraatomic molecule. Ooh, fancy. Yeah, tetraatomic means it comes as 4 atoms joined together. It likes to do that to share electrons and get full outer shells. So we give it the symbol P4 when phosphorus is in its elemental form. So you're just going to react P4 with O2, oxygen. So it's going to be P4, phosphorus oxide, and then we just got to work out how many oxygens. Well, if phosphorus has an oxidation state, well, if you think about it, it's in group 5. Now, it's not as electronegative as oxygen. So, yes, it can be a minus ion sometimes, but in this situation, it's a +5 ion. It's going to give away those 5 electrons. So, as there's 4 of them, it has a total of +20 as its oxidation state. Each oxygen atom is -2, or each oxygen ion will form a -2. We need a total of -20 to cancel out the +20, so I'm going to need 10 oxygens. So the equation is P4 plus O2 makes P4O10. Okay, sometimes it can be a bit confusing because people use the symbol P2O5 and say phosphorus pentaoxide, but phosphorus oxide doesn't actually exist like that. It's kind of a decaroxide like this. It always is in P4O10. Okay, let's move on. So, yeah, once again, that fancy name, tetraatomic molecule, is what we use for the P4. But let's move on. Give it an equation for the reaction between sulfur dioxide and water. So I need to write SO2 plus H2O, draw a little arrow, and that's going to make hydrogen sulfate, so H2SO3. And yeah, it's made of 2 hydrogen ions and the SO3 ion. You could write that as 2H plus SO3 2 minus, because that hydrogen sulfate in solution, as it says in water, is going to be aqueous, so the ions are going to be free to move. Again, here give the displayed formula for the anion formed when sulfur dioxide reacts with water. So sulfur trioxide, sorry. So SO3 plus H2O. This time it goes to H2SO4, sulfuric acid. We're looking at what's the anion in that. Well, the hydrogen ions are positive, or anion means a negative ion. I think of the AN as a negative ion. Okay. So you've got 2 hydrogen ions floating about. They're cations, they're positive ions. What we're looking at here is what is the negative ion. So the negative ion is going to be SO4 2 minus. What does that look like when we draw its structure out? Well, you need to know this off by heart, the sulfate ion. So you've got 2 double bonded oxygens and 2 oxygens with a negative charge, like that, with a single bond. That's the negative ion they want you to draw. Now, it's also possible to say that it exists as a ion which has only one negative charge, because one of those hydrogen ions could bond. So we could end up with SO4H SO4 minus. Okay, so we could have the hydrogen sulfate ion, and it could be HSO4 minus, and then you have another hydrogen ion loose. So that combination would also form a negative ion. So that is a possibility as well. So here we go. This is the other possibility. You've got one of the hydrogen ions has joined on, taking away that oxygen with a minus to form an OH. And there we go. You'd have one hydrogen ion left over, which is the cation. So that's a possibility. So either of those could be the negative ion present. Okay, so we're on to the last 2 bits. We have 3.4, give an equation for the reaction of magnesium with steam, and state an observation. That means something physically that you will see. So the equation would be magnesium, which is solid, That is going to react with water. As it's steam, it's going to be in the gaseous state, so we need to put a G. Draw our arrow. It's going to form magnesium oxide, and it's going to release hydrogen gas. And why is this different than other metal reactions? Well, other metal reactions form hydroxides with water. Think back to your GCSE, your alkali, your group 1 metals, they form hydroxides. So do a lot of the group 2s. But magnesium with steam will form magnesium oxide. Now, for the observation, just a warning, don't put you're going to see bubbles. Not that they accept bubbles at A level. You have to say effervescence. But you're not. You can only see bubbles or effervescence if there is either water or aqueous solution present. And as you can see from the state symbols, we don't have an aqueous solution or liquid present. So you wouldn't be able to see the bubbles of hydrogen gas as it forms. So don't put effervescence. Right. So what is a possible observation? So right, you're going to get 1 mark for the observation. We've already scored 1 for the equation. So we can say we'd see a grey or white solid form because magnesium oxide is grey or white. And also, when magnesium reacts like this, just like when you burn magnesium in a Bunsen burner flame, you're going to see a bright light, or you can say you're going to see a white light. So white light or bright light. Cool. And either of those will get you that extra mark for a maximum of 2 marks for 3.4. Right, 3.5, final bit of this question. Give an equation to show how an excess, that means extra, more than you need, of magnesium oxide reacts with phosphoric acid. So remember, phosphoric acid, just showing you the ions here, it's got H plus ions and PO4 3 minus. Biologists all know that from DNA. So you take your phosphoric acid, and that is our acid. We're going to react it with magnesium oxide. What is magnesium oxide? It's a base. Acids are always aqueous, by the way. If you're including state symbols, which it doesn't ask for here, acids are aqueous. So we've got our acid, we've got a base, and you'll remember from GCSE, acid plus base makes salt and water. So now the easy bit's coming up with the water, H2O. The difficult bit is coming up with the name of the salt. Well, if it's magnesium oxide and it's phosphoric acid, we're going to get magnesium phosphate. And you probably could work that out. Now you just got to work out the formula. Magnesium is a 2 plus ion because it's in group 2. And phosphate it's got a 3 minus charge. So if I want to balance that up, I'm going to need 3 magnesiums and 2 phosphates. So Mg3, PO4 in brackets with a 2. If you don't put the brackets, it will look like 42. And water. Well, now we need to balance it up. So I need 2 there to make the phosphates double. And I'm going to need a 3 in front of magnesium oxide so I can get my 3 magnesiums. And that leaves me with 6 hydrogens on the phosphoric acid. So I need a 3 here on the water. How many marks did you get out of 6 on that question? Question 4. Nitrogen dioxide decomposes at a high temperature. We've got 2 molecules of nitrogen dioxide in a reversible reaction to form 2 molecules of nitrogen monoxide and oxygen. It's an endothermic reaction. We can see by the enthalpy change of plus 113. And we have 0.137 mole sample of nitrogen dioxide, which is placed in a sealed flask and heated at a constant temperature until equilibrium. At equilibrium, the flask contains 0.120 moles of oxygen. Calculate the mole fraction of each substance at equilibrium. Right, so I'm doing the ICE technique where you write initial moles, change in moles, and the moles at equilibrium. We know the initial moles of nitrogen dioxide is 0.317. We know there must be 0 of the products. We know that the oxygen is 0.120 at equilibrium, which means that it has changed by 0.120. We now then look at the ratio to find the change in the other substances. So we look at the ratio of, say, oxygen to nitrogen dioxide and oxygen to nitrogen monoxide. So we know that the nitrogen monoxide is 2-to-1 ratio with the oxygen, so it's changed by 0.240, and that means that it has become 0.240 because it's gone from 0 to 0.240 equilibrium. We know the nitrogen dioxide has also changed by 0.240, which means if it's changed by 0.240, that it has decreased by 0.240. So what we've now calculated is the moles of each substance at equilibrium. So we've scored a mark here. We've got 0.077 moles of nitrogen dioxide, 0.240 of nitrogen monoxide, and 0.120 of oxygen. However, we need to write the mole fraction. And the mole fraction is the moles of the individual substance at equilibrium divided by the total moles at equilibrium. So we need to do, for example, if I want to find the mole fraction of nitrogen dioxide at equilibrium, I need to do 0.077, and I should divide that by the total moles at equilibrium. Now, the total moles at equilibrium, I need to add 0.077 to 0.240 to 0.120, and that equals 0.437. And so if I divide the individual moles by the total moles, I get 0.176, and that is my mole fraction of nitrogen dioxide. Now, a common mistake here would be to divide each of these sets of moles at equilibrium over 0.317, thinking, well, the total moles must be the 0.317 at the start. But of course, at equilibrium, the total amount of moles is different. It adds up to 0.437. So make sure you don't make that mistake. Okay, 0.240 over 0.437, we got 0.549, and that is the moles of nitrogen monoxide. And finally, 0.120 over 0.437, we get 0.275 moles, and that is the moles of oxygen. And there you go. You got your 3 marks. Lovely. Okay, let's move on. 4.2, zooming in. The total pressure in the flask in question 4.1 is 120 kilopascals at equilibrium. Calculate the partial pressure in kilopascals of nitrogen dioxide. If you were unable to answer the questions 4.1, you should assume the mole fraction of nitrogen dioxide is 0.380. Well, we did work it out in the previous question, and we worked out that the mole fraction of nitrogen dioxide was 0.176. So you just have to do the mole fraction times the total pressure to get the individual pressure of that gas. So 120 kilopascals is the total pressure times the mole fraction, 0.176, and you get the pressure of nitrogen dioxide. Right, 4.3. Table 1 shows the mole fractions of 3 gases in a different equilibrium mixture. Okay, so we've got the same equation here, and a reminder that it is endothermic. For this equilibrium mixture, Kp is equal to 59.7 Kp. Give an expression for Kp for this reaction. Use your expression in the data in table 1 to calculate the total pressure in kPa in the flask. So we've got a 3-mark question here, and the first thing up is to write an expression for Kp. Well, Kp, just like Kc or Ka or any other of these constants, is products divided by reaction. Sorry, products divided by reactants. So what we need to do here is write the products, and that is nitrogen monoxide, NO, to the power of 2, outside the brackets. Remember, when you're using Kp and you're using gas pressures, we are doing round brackets. Well, we can do 0.460 to the power of 2, and we can also, and that's the total pressure times that mole fraction. So I could put a P here, P times 0.460 to the power of 2, and then P times 0.230. And then I can divide that by the reactants, which is 2 lots of nitrogen dioxide. So we're going to put bracket 0.310 to the 2 in the top corner there. And that is our Kp, which is 59.7, and that's what it should equal. Now, the next part to the question says use your expression and the data in table 1 to calculate the total pressure in Kp in the flask. So all I need to do here is plug these numbers in, and I need to, first of all, rearrange. So I'm going to rearrange this, and we're going to be able to work out the total pressure. So essentially, we can cancel out you'd have total pressure times each mole fraction. You can cancel out and then rearrange to make total pressure the subject of the equation. And if you do that, you're going to get Kp times the mole fraction of NO2 over the top of the mole fraction of the products. And if you plug that into a calculator, you're going to get the correct answer. So essentially here you want to do 59.7 times 0.310 squared, divide that by 0.460 squared times 0.230. And if you do that, you're going to get 118, between 117 and 118 kilopascals, so rounded to 118 kPa. Okay, let's move on. Right, 4.4. The equilibrium mixture in question 4.3 is compressed into a smaller volume. Deduce the effect, if any, of this change on the equilibrium yield of oxygen and on the value of Kp. So compressing gases into a smaller volume is going to increase the pressure. And what do we know about pressure in Le Chatelier's principle? It's going to oppose the change. We're going to shift to the side with the least gas molecules, and that's the left-hand side. And so what's going to happen there is we're going to get a decrease in the yield of oxygen. So the yield of oxygen decreases, but what we'll find the effect on Kp is going to stay the same. Remember, Kp is literally just a ratio. So if you've decreased the yield of oxygen, the Kp will stay the same. Okay, so let's just have a little look at the next question, which is going to be 4.5. Make sure you hit the like, subscribe to the channel, and share if you want more of these videos helping you through your A-level chemistry. Okay, 4.5, the equilibrium mixture in question 4.3 is allowed to reach equilibrium at a lower temperature. Explain why the equilibrium yield of oxygen decreases. Well, remember, the reaction was endothermic. We had that plus 113 kilojoule per mole. So if you decrease the temperature, it's going to favor the side, or favor a shift to the side that will counter the change. What side will counter the change? Well, it will be the exothermic side, which is the reactant side, and favoring that direction will raise the temperature back up. So if you decrease the temp, the reaction looks to do the opposite and increase the temp. Remember Le Chatelier's principle, it will change or oppose your changing conditions. So if you decrease the temp, the reaction will look to oppose that by going to the side that will increase the temp. And that's going to be the exothermic side of the reaction, the side that releases energy. We've been shown in the reaction that it's plus 113 on the right. So it's going to shift to the opposite side to that, which is the reactant side, or backwards or to the left. You can say either one. Awesome. Okay, welcome to Let's Get to the Marks. This is question 5 of the 2023 Chemistry A-level paper for AQA, and it's on the Born-Haber cycle. So this question is about metal chlorides. Table 2 shows some enthalpy data. We got the enthalpy of hydration for calcium 2 plus ions and for chloride ions, and then we have the lattice enthalpy of formation for calcium ions. Calcium chloride. User data in table 2 to calculate the molar enthalpy change when you dissolve calcium chloride. Now, do you know what that's called? That's called the enthalpy of solution when you're going to dissolve something. So we're kind of looking at a Born-Haber cycle. This whole question is about the Born-Haber cycle, but for enthalpy of solution, you do very similar to your Hess's law, how you set that out. So we've been given the hydration of calcium 2 plus ions and the hydration of chloride ions. The hydration is when you convert them from gaseous state to their aqueous state. And we've been given the energy change for that. And I've circled those in blue here. Now we've also been given gaseous calcium and gaseous chloride coming together to make a lattice, solid calcium chloride, which is an ionic lattice, and that's minus 2237. That's the enthalpy of lattice formation. So we can now set this out and do a little calculation to work it out. So what the question's asking us is how much energy, or what is the enthalpy change when you take calcium chloride solid and we dissolve it basically into calcium 2 plus aqueous and calcium and chloride ions aqueous. We've got 2 chloride ions, by the way. So that's what we're looking for. So now we've got to try and use this data. Well, we've got the enthalpy change of solution that we're trying to find out, which is basically the energy change when you dissolve an ionic compound. So what have we been given? Well, we've been given calcium gaseous to calcium aqueous, which is the hydration of calcium. We've been told that that's minus 1650. We've also been given chloride gaseous to chloride aqueous, and we've been told that's minus 364. I'm circling these here. So we can write these out here and we can put those numbers in. Now we know the arrows go up. You just follow the arrows as they are in the table. So you create the arrows like they are in the table once you've set out your equation at the top for dissolving calcium chloride. We have to remember there are two chloride ions, and the data in the table doesn't have a 2 in front of it. It's only per mole. It's for one chloride ion. So we need to times minus 364 by 2. So now we've set that data out, lovely jubbly. We'll circle that there. We're going to come over here. What do we do over here? Well, this is a bit unusual. We've been given the formation of calcium gaseous and chloride ions in the gaseous into the lattice. This is the lattice enthalpy of formation, and it's minus 2237. And I'm circling that here. This is minus 2237. So we write that in here. Now, what we can do with these numbers is we know, remember Hess's law, it doesn't matter which route you take, the overall energy change is the same. So if I want to find out that top route with the question mark, I just draw an arrow going round here. I've chosen a lovely purple color. We're going to draw an arrow going all the way around, and we're going to go in this direction, and the overall energy change will be the same. So let's just look at those arrows. Now, wherever my pink arrow or purple arrow goes against the other arrow, you reverse the symbol. And that's because this is actually going from the lattice formation energy. We're changing this into lattice dissociation enthalpy. So it's the opposite. So it's plus 2237. Because look at my arrows, they're going in opposite directions. Now my purple arrows go in the correct direction with the enthalpy of hydration. So we're just going to go 2237 minus 1650, or plus minus 1650, however you want to write it, plus minus 364 times 2. Smash that all in your calculator, and you're going to get your answer for 2 marks. And you should get an answer of 100 minus 141 kilojoules per mole. And there you go. And don't forget, it's best to pause the video with each question and have a go before unpausing and watching my walkthrough. Okay. You can find all of these exam papers and these questions on the AQA website. So good place to go. Physics and Maths Tutors, another fantastic site where you can find most of the materials I go through with these walkthroughs. All right, let's move on to the next question. This is 5.2. Use your answer to question 0.05.1 to deduce how the temperature changes when calcium chloride dissolves in water. So what did we learn about that enthalpy of solution, which is the energy when we dissolve calcium chloride? What we learned is that it's minus 141 kilojoules per mole. What does the minus tell you? That tells you it's an exothermic reaction. That negative enthalpy change tells you it's exothermic. That means energy is released. So what's that going to do to the temperature? That's right, it's going to increase the temperature. The energy release will increase the temperature of the solution. So we'd expect a temperature rise. And there you go. That's your mark. Right, let's look at 5.3. Explain why the enthalpy of hydration of fluoride ions is more negative than the enthalpy of hydration of chloride ions. So if you hydrate, chloride ions were minus 364. So they're basically saying fluoride ions will give you a bigger number, like minus 500 or minus 400, but bigger than minus 364 when you hydrate gaseous fluoride ions to aqueous. Why is that? Well, think about the only difference you can think about. They're both in the same group, same electrons in the outer shell. So what's the difference? Chloride ions are a lot bigger. Fluoride ions are smaller. Okay, they have less electrons, less shells. And what that means is that the fluoride ions have a higher charge density. That negative charge is spread over a smaller area, making them more impactful. And what that means is that they have a stronger attraction to positive things. Now, what's positive on a water molecule? You got it. The hydrogen part of a water molecule is delta positive. Now, don't say the hydrogen atom is positive, because that would mean that water is an ionic compound. It's not. So water's a covalent molecule, but we know that the hydrogen is slightly positive. We use that delta positive sign. And what that means is that there's a stronger attraction between the fluoride and the positive, slightly positive hydrogen on a water molecule than there is between a chloride ion and the hydrogen on a water molecule. And there we go. So basically, the fluoride ions are more energetically stable. form a more energetically stable bond with water, therefore releasing more energy. So they're more thermodynamically stable when they bond with water molecules. And that's why their enthalpy of hydration is more negative. Okay, coolio. So that's 5.3. I hope you like, share, subscribe, and all that business as we move on. So make sure you hit the like. It's a little bit of a pain in the butt, I know, hitting the like button, but it really helps out the algorithm reach other A-level students and people that might be looking for this material or that find it helpful. Obviously, if you don't find it helpful, don't hit the like. Anyway, yeah, just showing you here. Here's a fluoride ion bonding with a hydrogen ion on a water molecule. And of course, there's a chloride ion badly drawn bonding to a hydrogen on a water molecule. And that's going to be a weaker attraction with the chloride ion than you'll get with the fluoride ion. And the reason is fluoride is smaller, so it has a higher charge density. Okay, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
5.4, figure 2 shows an incomplete Born-Haber cycle for calcium chloride. So you've got one of these. People find these really difficult, but Born-Haber cycle, here we go. Right in the missing formulas. So you can see there's two blank lines, one right at the top and one in the middle there. Well, what we've got at the bottom there is the lattice formation enthalpy, and then we've got going up from that, we've got calcium solid plus chlorine gas. You can see here the first one, and as we move up, what we're going to do, we're going to turn those calcium solid into gaseous calcium. What do we call it when you turn an element from its natural form into its gaseous form? And that is going to be the enthalpy of atomization. So we're atomizing the calcium atoms. They're being atomized. Now, so you need to write that out. CAG in gaseous form plus Cl2 still in gaseous. Now, as you go up to the next stage, what have we done? We've ionized the calcium to 1 plus. So that's the first ionization energy of calcium. And then we've got the second ionization energy of calcium if we go to the level up, because it goes to calcium 2 plus 2 electrons. But our chlorine gas is still a molecule. Have a look here. I'm going to circle it here. That is still a molecule. It's not been atomized yet. Yes, it's in gaseous form, but it's in molecular form, not atomized. So our next one at the top here, we need to write out an equation to show the atomization of chlorine. We need to keep the calcium as 2 plus. We're not reversing any of it. So we remove those 2 electrons. We're just changing the chlorine from a molecule to atoms, and you put 2Cl in gaseous. Now we haven't ionized the chlorine yet, so they're still atoms, they're not ions. That happens in the next stage as you go down on the right, and that's called the electron affinity of chlorine as those chlorine atoms gain electrons to become chloride ions. All right, that'll get you your 2 lovely marks. Let's move on to the next question. Now I've kept the equations here because we're going to need it for this question. So I've kept all of those that we've just written in, and this is 5.5. Table 3 shows some enthalpy change data. We've been given a bit of data that matches every single one of these equations on the left here on the Born-Haber cycle. We're just missing one, and they want us to calculate the second ionization energy of calcium. So if we go to the one just before the top, I'm going to circle it in blue here. This is the second ionization energy. That's the only one we don't have data for. So what we want to do is write the data in for all of the others and then try and work out that missing one, okay? So this is our second ionization energy of calcium. So what we're going to do, we're going to go to this data on the right-hand side and write all the numbers into the correct places. So I'm writing 193 here, and that's because that is the atomization of calcium. 590 there for the first ionization energy of calcium. We don't know the second IE. We know that 121 is for the atomization of chlorine, and minus 364 I've written in red for some reason. That is the electron affinity of chlorine. And remember, it's per mole, so you have to take account of wherever they put a big 2 or a coefficient on the equation. You're going to need to multiply in those situations, wherever there's a coefficient. And then we have minus 795 here. This is for the lattice enthalpy of formation of calcium chloride. Sorry, the enthalpy of formation of calcium chloride, and minus 2237 is for the enthalpy of lattice formation of calcium chloride, and that's on the right. Now, what we're going to do here, what you need to appreciate is that we can set this out as minus 795, the arrow going down, is equal to everything else in the opposite route. So the enthalpy of formation of calcium chloride is equal to, if you then follow up with your finger and go all the way round the other side, it's equal to all of that. So I've drawn an orange arrow here, and this shows that that minus 795 is equal to everything along that orange arrow. So we just got to write it all out. Minus 795 equals 193 plus 590 plus second ionization energy plus 121 times 2. Now, why am I timesing 121 by 2? That's because there's a coefficient of 2 in front of the chlorine, and then plus minus 364 times 2. Why am I doing times 2? Because there's 2 chloride ions, and remember, it's per mole. I've circled that in red on the table, the data table. And so all we need to do, and minus 2237, all we need to do is now simplify to work out what the second ionization energy is. So I'm going to add together all the positives to make 783, 193 plus 590. I'm going to multiply minus 364 by 2 and 121 by 2. And then we're going to simplify that out each time. I like to do it step by step because I'm going to make mistakes. Some people just bash this all in their calculator, do it all in one go. So I've now got 1025 plus the second ionization energy plus minus 728 minus 2237. So I'm going to add those minuses together. I'm going to get minus 2965. Now all I want to do is take the 1025 and add it to the minus 2965, and we're going to find that minus 795 equals the second ionization energy minus 1940. So what do I do now? I just plus 1940 to each side. So I'm going to plus 1940 to each side, and that means we're going to get rid of the 1940 on the right hand side to just leave second ionization energy, and you're going to take 1940 and add it to minus 795, smash that in your calculator, and you're going to get your answer, which is going to be 1145 kilojoules per mole, and that is the second ionization energy of calcium. And we know the first ionization energy was plus 590. Were we expecting a positive answer? Yes. Look at the first ionization energy. It's positive. So you would start to think the second one must be positive too. So you can use a little bit of lateral thinking to check if your answer's right. Explain why the second ionization energy of calcium is greater. So why was it 1145 compared to 590? Why was it that much greater? Why is it harder to remove an electron the second time from calcium? Remember, it's in group 2. So the answer is that you're taking an electron that is away, that is going to be slightly closer to the nucleus. Why is it closer to the nucleus? Because there's a greater positive charge on a calcium plus ion, so that electron is going to be drawn in slightly closer to the nucleus. So the second electron's closer to the nucleus, or you could say here you're removing an electron from a positive ion, which you weren't before, so which has an overall positive charge. So there's greater attraction between the electron and the nucleus. Coolio, and either of these two would get you a mark. Either of those two comments there. Right, let's move on. We're nearly done with this question. So we just got a disgusting 6-mark question, which I don't have a lot of space to fit in, but let's go for it. Table 4 shows the lattice enthalpy on a perfect ionic model and lattice enthalpies from the Born-Haber cycles for 3 metal chlorides. So we've got calcium chloride, potassium chloride, silver chloride here on the left-hand side of the table. We then have their enthalpy of dissociation when you look at the perfect ionic model. Okay, so when you assume that they are spheres, that is what the perfect ionic model is. It assumes that they are complete spheres. On the Born-Haber cycle is where you do the calculation, and we can see that we can compare the two. They're never exactly the same. Now, compare the 3 values based on the perfect ionic model. Compare the values based on the perfect ionic model to the values from a Born-Haber cycle for each compound. So the first thing we need to do, check out that keyword compare. Compare the 3 values on the perfect ionic model. So do that first. Which is the highest? What's a basic description? Right, calcium chloride has the largest perfect ionic model, or the largest lattice enthalpy when we consider the perfect ionic model. In fact, it's much larger than potassium chloride and silver chloride, which are quite similar. So I might want to say calcium chloride has the largest, potassium chloride and silver chloride are quite similar, their values. Why is this? What do you know about calcium ions compared to potassium and silver ions? Well, calcium ions have a +2 charge. Therefore, we're assuming that the ionic bond is stronger between a calcium ion and a negative chloride ion because, of course, there'll be a stronger electrostatic force of attraction between the calcium ion and the chloride ion. So we can assume that calcium chloride has stronger ionic bonds than the other two metal chlorides. And why is that? Potassium and silver are both K plus and Ag plus. So we would assume there that they have weaker ionic bonds, and that would get you all the marks for talking about comparing the perfect ionic model values. So you're just looking at that set of values separately on the left hand side for this first part of the question, and you're explaining why the calcium chloride has a bigger number than the other two. Now we need to consider the perfect ionic model to the values from the Born-Haber cycle. So now we need to look individually going across in a row. Calcium chloride go 223, whatever it is, 2223 to 2237. So what can we say about calcium chloride's perfect ionic model enthalpy to its Born-Haber cycle lattice enthalpy of dissociation? That's what we have to think about for the next part of the question. Okay, so yeah, don't forget to hit the like. It helps with the algorithm, people getting into this channel. So yeah, you can see there, potassium chloride, silver chloride have similar perfect ionic models. This because they're both +1, both have similar strength ionic bonds. Anyway, getting on to the second part of the question that I've been whiffling and waffling about. What we're looking at now is compare the values based on the perfect ionic model to the values from a Born-Haber cycle for each compound. So if we look at calcium chloride, it has 223 and 2237, only 14 difference between the perfect ionic and the Born-Haber value. And if we look at potassium chloride, there's only a difference of 11, 690 to 701. So what we can say is for calcium chloride and potassium chloride, they have similar perfect ionic to Born-Haber values for the enthalpy of dissociation. Now, why is that? That's because these are spheres. They obviously are spherical ions, and therefore their values are very similar. However, when we look at the silver chloride, which is 770 for the perfect ionic model, and 905 for the Born-Haber lattice enthalpy of dissociation, what we can see is there's a big difference. What's that? That's 130, 135 difference. Okay, so why is there a big difference in the lattice enthalpy of dissociation for the Born-Haber? Why is it higher? And this is because silver chloride must show some covalent character. Covalent bonds are normally slightly stronger than ionic bonds, and therefore we've got an increase in the expected strength of the bond. And this is because the Ag plus ion must be very polarizing and so distort the electron cloud around the chloride ion, preventing it from being a sphere, basically. So what we have is non-spherical ions. Because Ag plus is very polarizing because of its high charge density, it's distorting the chloride ion electron cloud and pulling it in towards the Ag plus. So we're getting some covalent character. We can say it's not spherical. And all of these things are going to pick you up marks and help explain why there's that difference between the perfect ionic model lattice enthalpy of dissociation and the Born-Haber. All right, guys, that's enough from me. So don't forget, subscribe to the channel and carry on watching. Let's get to the marks. Okay, we're going to take a look at question 6. The concentration of dilute hydrochloric acid can be found by titration using a standard solution of barium hydroxide. 6.1. Calculate the mass in grams of solid barium hydroxide, MR of 171.3, needed to prepare 250 centimeter cubed of 0.1 mole per decimeter barium hydroxide solution. This is worth 1 mark, and they want the answer in grams. Let's go. First of all, the question has asked us to calculate, so we know we're doing some maths here. It's given us the MR, and it wants us to find the mass in grams. So what do we know about mass in grams? Well, for mass in grams, you need to do MR times moles. You should know this off by heart from GCSE. So mass over MR times moles. I use that little n, lowercase n for moles. The second bit of information, we've been given the volume and concentration of a barium hydroxide solution. So you should also know the magic triangle from GCSE, number of moles over concentration times volume. So now what we need to do is use the concentration and the volume to find the moles, and then put the moles over in the second triangle, times it by the MR, and we'll get the mass. So let's have a go at that now. So don't forget, when you get centimeter cubed, you need to divide by 1,000 to put into decimeter cubed. So we're going to do 250 divided by 1,000. We're going to multiply that by 0.1, and that's going to give us our number of moles, which is lowercase n. We're then going to multiply our number of moles by the MR, which is 171.3, and that's going to give us our mass in grams. So 0.025, which is our moles we found from volume times concentration, and we're going to multiply that by 171.3, which is the MR of barium hydroxide, and now we're going to get our final answer, which is in mass, and it works out like 4.285. Okay, 4.285 grams, and there we go. Now let's move on. So for 6.2, the mass of barium hydroxide from question 0.61, that's 4.285, is dissolved in a beaker containing 150 centimeter cubed of distilled water. Describe, notice the word describe is different than calculate. So this is a written answer, even though we might make the mistake and think we need to do a calculation here. That should trigger you into realizing it's a written answer. Describe how the solution is used to make 250 centimeter cubed of 0.1 mole per decimeter barium hydroxide solution. So they actually want a description, not a calculation, even though there's some numbers here. So what we want to do is say, add the solution to a volumetric flask. Okay. Volumetric flasks have a mark, so we want to make that up to the mark by adding distilled water. Include all your washings. So that means get some distilled water and rinse out the beaker or whatever you made the original solution in, and tip all of that in so you haven't left any of the 4.285 grams left behind in your apparatus. You want that all to enter the volumetric flask. And then you're going to put the stopper in and invert several times, which means turn it upside down. You don't have to use the word invert, but basically rotate, turn it around once the stopper's in, and that's going to evenly spread the mass. And there you go. You've now got a solution. Oh, let me just add that in. I forgot to add the washings in. And there we go. So let's move on to the next part of the question, which is going to be 6.3. 6.3. Before the first titration, the 25 centimeter cube pipette is rinsed with a small volume of 0.1 mole per decimeter barium hydroxide solution. State why it's a good practice to rinse the pipette in this way. So we're not talking about a dropping pipette, we're talking about the volumetric pipette, the one that measures exactly 25 centimeter cube that we use for transferring solutions. Now, if we're going to put in it the known concentration, we mustn't rinse it with water. If we wash this pipette with water, it's the known solution. We're going to dilute it. And this means it's no longer going to be a known solution. It's going to have a lower concentration than we thought. Also, there might be some water left over in it. So you should always wash it with some of the known solution. That way, you're not going to alter the concentration at all. So wash it with the known solution. You won't alter the concentration. It will get rid of any water or any impurities in the pipette without diluting the concentration of the known. Of course, when you're dealing with the unknown solution in a titration, you can rinse and should rinse with distilled water, as you won't affect the amount of moles in there. All right, let's move on to 6.4. Hydrochloric acid is added to the burette using a funnel. State why it's good practice to remove the funnel from the burette before the titration. So let's have a little look. Okay, if you leave the funnel in there, which has got hydrochloric acid in it, as you do your titration, some hydrochloric acid might drip from the funnel into your burette. This means you'll get an underestimation or undervaluation of your titra. So you might think you've added 25 centimeters, but actually you've added 26 centimeters, and 1 centimeter dripped in from the burette and made you think from the funnel, 1 centimeter dripped in here in pink, and made you think you'd only added 25 instead of 26. So you'll get an undervaluation if you leave the funnel with some acid or alkali in, dripping into your burette. So that's why we got to remove the funnel before we open the tap and start the titration. Now that'll get you 1 mark. So let's move on to 6.5. In a different experiment, 0.952 grams of solid barium hydroxide is used to make 250 centimeter cubed of standard barium hydroxide solution. I can't even speak. 20 centimeter cubed of this barium hydroxide solution reacts exactly with 24.50 centimeter cubed of hydrochloric acid. Calculate the concentration of the hydrochloric acid. So what we want to look at here, we've been given some volumes here, which I've labeled V. I might want to label this M for mass. I've been given another volume over here, 250 centimeters. What I'm starting to gather here is that I'm going to need those triangles again, that N over C times V, and I'm going to need M over MR times N as well. So I'm going to need my triangles. The question is, calculate the concentration of the hydrochloric acid. So we're probably going to need to know the ratio. Whenever you're going to use moles, you're likely, and there's a reaction going on, you're going to need to know the ratio between the reactants. So let's work out the ratio between the barium hydroxide and the hydrochloric acid in this reaction to start with. Also, check this out. They'll always do this in titrations. They take a large volume, like 250 centimeter cubed, and then we're going to titrate just a 25 centimeter sample. This means when I work out the moles of that barium hydroxide, it's 10 times smaller than it should be. So we're going to work out the moles in the 25 centimeter, and then we're going to need to times by 10 to work out the total moles in the 250. All right, let's look at this equation. Barium hydroxide plus hydrochloric acid goes to barium chloride and water. Basically, base and acid make salt and water. We can see it's a 2-to-1. So for every mole of barium hydroxide we've got 2 moles of hydrochloric acid. So which one of these can we work out first? So we can work out our moles of barium hydroxide. And we can do that by doing 0.952 grams and divide it by that MR they gave us in one of the earlier parts of this question, 171.3. And that gives us 5.56 times 10 to the minus 3 moles of barium hydroxide. Now that was in the 250 centimeters. What we have to remember actually is that we only used a tenth of this. Okay, so actually we need to divide that by 10 because it's going to be a smaller amount that we actually used. We took 1/10, 25 centimeters from the 250. Sometimes you've got to times it by 10. In this particular question, we have to divide by 10 because we're taking a tenth of those moles in the 0.952 grams. So we're going to divide by 10. Then that's our moles of barium hydroxide. And that gives us 5.56 times 10 to the minus 4 moles of barium hydroxide. Now we know that for every mole of barium hydroxide, I've got 2 of hydrochloric acid. So we want to multiply that by 2, okay? And that is going to give us 1.112 times 10 to the minus 3. And that's our moles of hydrochloric acid. Now what we want to do is do N over CV. So we're going to do moles of hydrochloric acid divided by the volume of hydrochloric acid. Now the volume of hydrochloric acid was 24.50 centimeter cubed. Don't forget to divide by 1,000. You need to convert to decimeters. And that is going to give us our concentration of hydrochloric acid. By doing N over V, we get C, and it is 0.00453. What's that? 8. Well, we can just call it 0.045. And that gets us 3 marks. So let's move on. 6.6, the final part to the question. All right, 7.1, give the electronic configuration of the Al3 plus ion. Well, if we look aluminium up in the periodic table, you're going to see that aluminium, I think the numbers are 27 and 13. So we go, first of all, work out what aluminium is, go 1s2, 2s2, and then with each new quantum level, you add another orbital subshell. So we got 1s2, then it goes 2s2, 2p, and of course 6. And then we go 3s2, and then we go 3p. Now it can't have 6 because there's only one more electron to add, so 3p1. So that is the electronic configuration of an aluminium atom. As it's a +3 ion, it's going to lose 3 electrons. So our electronic configuration is 1s2, 2s2, 2p6. Hopefully you got that correct. All right, let's look at 7.2. When anhydrous aluminium sulfate is added to water, a solution forms that contains the complex ion Al H2O6 3+. Give the equation for the reaction. So one of the important things to do here is make sure that you read the question. And you can see here Al2SO43 is added to water and a solution forms. So we know the reactants and we know at least one of the products. Let's get down to it. So first of all, you just want to copy what's in the question. So Al2SO4, we need to put a 3 outside the brackets. It says it's added to water, so we want to go plus H2O. Now, it says a solution forms, so the water would have a liquid state symbol if we're going to bother with state symbols. But this is our solution, aluminium, and we've got H2O, close bracket with a 6, close the complex ion bracket, and put 3 plus on the outside. Now, we were given all that information from the question, so that is straightforward. The only thing we haven't been told is what to do with the rest of it. Now you can see there's 1 aluminium here and there's 2 over here, so I need a big fat 2 in front of this here. And that should inform us as to how many H2Os would I need. Well, I've got a big fat 2 here, which I had to put here because I've only got 1 aluminium and there's 2 there. So I've had to put a big fat 2 there. That means I've got 12 H2Os. 2 times H2O, 6. So I need a 12 in front of H2O here. And that's all looking good. What's the last thing that I need? Well, this side is charged because I've got a +6 charge. There's 2 times 3 plus, and this side there is no charge. So I need to balance the electronic charges. And if we look here, I'm missing the sulfate ions. So we've got 3 lots of sulfate ions. So I need to add in plus and then a big fat 3. And then we're going to do those sulfate ions that are over there. So that's 3 times SO4. And they must be 2 minus each. You should know that off by heart for the sulfate ions. And of course, that cancels out. You get -6 and +6, which would cancel out to make it neutral. Both sides of the equation are balanced. Whoopee-doo, we're done. Super. Hope that was easy to work out. Right, we're on 7.3 now. So 7.3, can't speak properly. Explain what a solution containing Al H2O6 3+ is acidic. So why is it actually acidic? This is actually because the aluminium 3+ ion, Al 3+ ion, has a high charge density. You can say, if you don't, I like using that term, I like using this term, high charge density, but you don't have to say that. You can say instead, aluminium ion is small and has a relatively high positive charge, i.e. +3. So we've got our protons spread across a very small volume, which of course you can explain by just saying it as a high charge density. Well, what does that mean? That means that it weakens the water molecules. Well, basically, it weakens the hydrogen-oxygen bond that's in the ligand, and then that hydrogen is donated to the water molecule. And that basically explains why it acts as an acid. So essentially, it weakens the bond in the ligands, uh, this means the hydrogen ion is released from ligand to the water molecule in solution. Okay, so essentially you kind of got the Al3 plus being super duper charged. You've got your ligands. Now the bond is weakened. This bond here gets weakened, and what happens is my water from the solution then picks up this hydrogen and becomes H3O plus, which can now release those hydrogen ions as an acid. So essentially, it all comes down to the aluminium 3 plus charge ion having a high charge density, and therefore it can weaken the OH bond, which means the hydrogen ions will be released. And that will get us our 2 marks. 1 mark for that, 1 mark for weakening the OH bond. Okay, let's move on. Okay, 7.4. Let's have a little read. State why the concentration of aluminium sulfate solution cannot be determined by colorimetry. And it's because aluminium sulfate solution is colorless. It has, oh my gosh, squeezing all this together. Look what it's got here. This is the Al3 plus electronic configuration. What do you notice? There are no partially filled d orbitals or no d electrons. What does that mean if there's no d electrons? It means there are no d orbital transitions. Transitions. Okay, what the hell does that mean? That means, so what happens when things give out color? If you have d orbitals of slightly different energy, when photons are absorbed, so if this lower orbital absorbs a photon, the electron can move from one d orbital to a slightly higher energy d orbital. We call that a d to d transition. And generally, the wavelength of the photons, the wavelength of those photons that are absorbed are complementary to the color that is observed. So the fact is that there are no d electrons, so there can't be any of these jumps between d orbitals, so therefore there won't be any color. And I hope that's clear, just like an aluminium sulfate solution. Haha. Right. 7.5. An excess of aqueous ammonia is added to a solution containing AOH2O6 3+. Give an ionic equation for the reaction and state one observation. So again, we're being told everything we need to know here. So have a little look. They're telling us we've got aqueous ammonia and it's added to this solution. Give an ionic equation for the reaction and say an observation. So let's first of all write out the equation. So we've been told we've got ammonia. Don't really need to put the 3 there yet. That will be part of the balancing. So we got the ammonia. We're told it's aqueous. So let's just put the state symbol in there. Then we're told it's added to this in solution. So H2O with a 6, close the bracket, put the 3 plus charge outside, aqueous. So we're told these are the reactants. Now we need to know, well, what is this going to make? And what we get a bit of ligand substitution here. So we're going to get H2O, oh my good gosh, with a 3 there. And then we're going to get OH3. Oh my gosh, running out of room. So, and I shouldn't have the 3 inside the brackets. That's going to lose me my marks. So let's close that bracket and put the 3 there. And what I need to do actually is select all of this. Oh my days. And drag this across because what I'm doing, oh my days. Yeah, that will give me a little bit more room to complete this equation. Nice. And so this is all going to be balanced. There's no overall charge in this molecule. There's no overall charge here because the Al3 plus ion is cancelled out by the three hydroxide ions. So we don't have a 3 plus charge. And as it was excess, what happened to those hydrogens that were on those three water molecules that have been broken down into hydroxide ligands? Well, they have joined with three ammonias because we had excess ammonia to make three ammoniums. So we have to have three ammoniums because those three hydrogens from these three water ligands that became hydroxides have joined with the ammonia, which means over here I need a three there as well. And here we go. That is our lovely jubbly equation. Now, what is our superbulous observation? Actually, the product complex formed is a solid, not aqueous, and we're going to see a white precipitate. So, because that's a solid there. Yeah, and that's it, a white precipitate. Right, let's move on to 7.6. So, let's go to 7.6. What have we got? An excess dilute sulfuric acid is added to the products of the reaction. Identify the aluminium species produced. So if we now add sulfuric acid back and we add it in excess, think about what we did up here. We added a base which removed and accepted hydrogen ions. Imagine we add hydrogen ions back to the solution. So we added a base, which was ammonia, to absorb hydrogen ions. Now we're adding hydrogen ions back. Guess what we're going to do? We're going to reform Al H2O6 because those hydroxide ions over here are going to pick up those hydrogen ions from the acid and we're going to reform. So there we go. And I need to close the bracket and put the 3 plus charge back. So adding the dilute sulfuric acid is redonating those hydrogen ions that were removed by the ammonia, and we go back to our original species. Super. Okay, let's look at 7.7. Figure 3 shows the structure of the EDTA4 minus ion. So you can see the structure here. Atoms of two different elements in EDT4 minus can form coordinate bonds with an aluminium ion. Well, figure 3 draws circles around the atoms of two different elements that would link to an aluminium ion by a coordinate bond. So the aluminium ion has a positive charge. You're looking at things that can donate electrons to it. So if we look at this structure, can you see any atoms or elements that have lone pairs of electrons? You should realize nitrogen, group 5 element. So this is in group 5. It's only got 3 bonds. And what does that tell you? It's got a lone pair. So we're looking at nitrogen being able to loan a pair of electrons to the aluminium and form a ligand or a coordinate bond. And you've also got, obviously, oxygen as well, has the ability to do that. Okay, super. So that'll get you your 2 marks. Now let's go on to the last part of this question, which is a big fat part. Okay, welcome to Let's Get to the Marks. We're looking at 7.8 of the 2023 Paper 1 A-Level Chemistry, and this is on hydrated salts, and it's all about working out the integer x, and it's a big fat question worth 7 marks, 7 whopping marks. So let's get into this one and check it out. Right, let's get this whole question in view. Hydrated aluminium sulfate Al2SO4 3.XH2O is soluble in water. The relative formula mass and value of X can be found from a titration experiment. Aqueous AlH2O6 3 plus ions react to form a stable complex when treated with an excess of EDTA4 minus ions. The excess EDTA4 minus ions is determined by titration with zinc sulfate. The method: dissolve 1.036 grams of aluminium sulfate hydrated in distilled water and make up to 250 centimeters. So straight away, look, we've been given the mass, and that is immediately making me feel like we are going to need our mass over mR times moles. And so we immediately want to note that as we go through. And it says make up to 250 centimeters, then add 25 centimeters from the 250. So what I want to know here is I've gone from 250 centimeters to 25. So I've kind of had a bit of a dilution here, or not really a dilution, but I've taken a portion. It's not really a dilution, but we've taken 25 centimeters of 250. So I just want a little note there, something that's going to trigger me later on to remember that. Of this solution, we're going to add that to 50 centimeters containing EDTA4 minus ions of a concentration of 0.01 mole per decimeter. Now, what have they given me? Mole per decimeter. What does that unit tell you? It tells you you're dealing with concentration. So I want to put on my second triangle here, which is N over C times V, because they're giving me concentration. So now we're starting to get cooking on gas. Determine the excess of EDTA4 minus ions by titrating with zinc sulfate solution in the presence of an indicator. The excess EDTA4 minus ions require 18 centimeters, that's our volume, and 0.0105 mole per decimeters to react completely. Look, I've been given a volume and a concentration, so we've got a great starting place here where we can work out moles. The equations for the reaction are hard. We got two equations. We got 1 and 2. So we've got two equations going on here. Whenever you get two equations in a titration, you're looking at what we call a back titration. And this is where you calculate the excess EDTA and you subtract it from the original volume of EDTA, which we can work out here. And what that does is that allows us to work out how much EDTA reacted in the first equation and work out your missing moles. So let's get into it. We've also been given the MR, which confirms we're going to have to use this equation here. So where do you start in a big dirty 7-mark equation like this? Well, there's a couple of starting points. We've been told we had 50 centimeter cubed of EDTA4 minus there. So I could actually calculate the original EDTA4 minus, or I could start down here at the back and work my way up. I tend to start at the bottom and work my way up. If you find these difficult, just start at the bottom and work your way up through the data. So that's why we call them back titrations. So start at the back. So I'm going to work out the excess EDTA4 minus, and we're going to do that. Let me change the color so it stands out a bit more. We've got volume times concentration equals moles. So I'm going to do 18 divided by 1,000 times the concentration of 0.0105. And this is going to give me my moles, which is 1.89 times 10 to the minus 4. Now, what this has told me, this is the moles of excess EDTA. So I want to label it as well so I know actually what I'm banging on about. So this is excess EDTA. Okay, I'm going to skip the 4 minus for ease. So that's the excess EDTA. If we go down to this equation, we can see that that's in a 1-to-1 reaction with the zinc. But actually, that was the zinc solution I've worked out. So getting myself in a muddle there. But that does tell me, it doesn't really matter because they're the exact same, but this was the zinc sulfate solution. And they are actually in a 1-to-1, as you can see there. So because they're in a 1-to-1, that also tells me I have 1.89 times 10 to the minus 4 moles of excess EDTA because they were in a 1-to-1. Now I know the excess EDTA. Let's work out the original EDTA by coming up here to the 50 centimeters with 0.01. And then I can subtract the excess from the original to get how much EDTA was used in this first equation. So we're going to do original EDTA was 50 over 1,000. Why am I doing that? Because we need to turn centimeter cubed into decimeters. And I'm going to times that by 0.01, and that is going to give me the original EDTA, which is 5 times 10 to the minus 4, and that is the moles of original. Now I want to find out the reacted EDTA. So reacted EDTA is equal to the original minus the excess. And so I want to do the original, which is 5 times 10 to the minus 4, take away 1.89 times 10 to the minus 4, and that is going to give me my reacted EDTA, which is 3.11 times 10 to the minus 4. So my reacted EDTA, this is how much was used up. So this is EDTA that reacted with AlH2O6, right? So that is how much EDTA reacted over here. Now we can tell that's a one-to-one. So that means I also know now that I had 3.11 times 10 to the minus 4 of AlH2O6, right? So that's how many moles of that I had. However, we're dealing with aluminium sulfate here. Look, aluminium sulfate. So what I need to know is that this one molecule of this aluminium complex ion only has one aluminium atom in it, whereas there are two aluminium atoms in aluminium sulfate. So if I want to find out how much aluminium sulfate produced this, I need to divide by 2 because, excuse me, these bad boys have two aluminiums in them. So these aluminium sulfates have two aluminiums. So I need to divide by 2. So let's do that. That's 3.11 times 10 to the minus 4 divided by 2. And that is going to give us 1.55 5 times 10 to the minus 4. So we're going to get, I have 1.55 times 10 to the minus 4, and that is my moles of aluminium sulfate. Now, we've worked our way up to here. Here's where the next problem is. The next problem is that this is in 25 centimeter cubed. That's how many moles of aluminium sulfate I have in 25 centimeter cubed. What I need to do is times that by 10 because we're looking at how many moles of aluminium sulfate were in 250 centimeters cubed. So let's times this by 10. And if I times by 10, we're going to end up with 1.55 times 10 to the minus 3 moles. And that is aluminium sulfate in 250 centimeters. I now want to turn that into grams. Now you might say, why do you want to turn that into grams? What I'm trying to do here, I know the total mass of water in aluminium sulfate was 1.036 grams. So if I can find out how many grams of that is aluminium sulfate, I'll know how many grams I've got of water, and then we can work out the moles of each. So this is my moles of aluminium sulfate, right? God, it's long doing this, and that is scrappy. That's my moles of that. Let's work out my moles of water. So I want to times this by 342.3 because this is the MR of aluminium sulfate. So times 342.3, and we're going to get, I have 0.53 grams of aluminium sulfate. So let's do 1.036. Let's take away the 0.53 grams, and we're going to find out how much of this Al2SO43.xH2O is water. So let's do 1.036, take away answer. We're going to find out that we have 0.503 or 504 grams of H2O. So how does this help us work out what X is? If we just look at mass for mass, it's almost a one-to-one in terms of mass, right? Because I've got 0.53 grams of aluminium sulfate and I've got 0.503 grams of water. However, that doesn't tell me what X is because X, okay, is going to be telling us the ratio of the moles of aluminium sulfate to the moles of water. So I need to compare my moles of aluminium sulfate, which is 1.55 times 10 to the minus 3 to my moles of water. Well, what are my moles of water? Well, I need to take the grams, 0.503 grams and I need to divide it by the MR of water. Hopefully you can remember the MR of water off by heart. You should know it now. You're doing A level. H is 1, O is 16. So I got two H's and an O. That is 18. So 0.503 grams divided by 18. And we are going to get, we have 0.027 moles of water. Okay, and I got this many moles of aluminium sulfate. So what's the ratio between those? Well, what I'm going to need to do, I'm going to come all the way down to the bottom left because I've run out of room, which is a bummer. And I need to divide the big number by the small number. So 0.027, I've got more moles of water than I have aluminium sulfate because this is 0.05155 or 1.55 times 10 to the minus 3. And then let's see what that ratio is. So I'm going to go 0.027 divided by 1.55 times 10 to the minus 3. And yeah, and we get roughly 18. So that tells us that there are 18 molecules of water for every molecule of aluminium sulfate. So although the masses were roughly equivalent of aluminium sulfate to water, we had about zero point 0.5 of each. When you convert that into moles, we've got 18 times more moles of water than aluminium sulfate, so X is 18. All right, welcome to Let's Get to the Marks. We're going through a question on fuel cells at the moment. So here we go. This question is about fuel cells. Where did I get this question? This is AQA Chemistry Paper 1, Question 8, 2023. So let's get into this one. In a methanol oxygen fuel cell, the overall reaction is methanol plus 1.5 oxygens goes to carbon dioxide and 2 moles of water. The EMF is plus 120 volts. 8.1. At the positive electrode, oxygen reacts with hydrogen ions to form water. Give a half equation. I always recommend you underline or highlight. These things are nice and easy. So we've been given the word oxygen. We've been told that hydrogen ions, we've been told that they react and they make water. So just write that out as an equation. Make sure when you do this, you leave a bit of space either side for balancing and adding electrons and hydrogen ions. So we got oxygen and hydrogen ions, because I never normally do that, and then it all becomes a mess. Arrow in the middle, leave a bit of space. And then that forms H2O, leave a bit of space. So was that it? Oxygen with hydrogen ions to form water. Beautiful. Right, let's balance this up. So if we look over here at our water, we've got two H's here and a 1H there. I could start there, but more importantly, I've got one oxygen here and I've got two here. So I'm going to start here. It's going to make it a little bit easier for me. I'm going to need to put a big fat 2 over here to make 2 oxygens. What's that going to do? That's going to mean that I need a 4 over here to make the 4 hydrogen ions. If I'd started by trying to balance the hydrogen ions, I'd have ended up putting a 2 here and then realizing I've got to balance the oxygens and rub it all out. So you could do a quick review in your head, but it doesn't matter if you just follow it through, but you'll just need to rub out a bit if you do that. Okay, now it's perfectly balanced in terms of the atoms or elements and ions, but it's not electrically balanced because I've got a positive charge on one side and a neutral charge on the other. So I need to get rid of this 4 plus, and the way to do that is to add 4 E minus. Of course, what does E minus stand for? It's shorthand for electrons. So by adding 4 electrons, this is now electrically balanced, and this is going to score you a mark. Boom. What I'd also do is note here in my head, when you're doing these equations, you fuel cells, or when you're doing electropotential, electrochemistry, basically, note whether it's oxidation or reduction. So what do you reckon? Well, these 4 electrons are being added or gained. And remember the oil rig from GCSE, oxidation is loss, reduction is gain. So we have reduction. So we've got our oxygen going to H2O. That is reduction. Super. All right, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving.
Right, 8.2. At the negative electrode, methanol reacts with water to produce carbon dioxide and hydrogen ions. So we've got a few more things going on here. What do they want? Give the half equation. So methanol, water, makes carbon dioxide and hydrogen ions. So we just want to write this out. Make sure you pause the video and have a go. That's what I like to say, with all my videos. So don't just watch me go through it. Have a little go on some scrap waste paper that you don't need, some of those old back of old notes or whatever. Just have a go when you go through the videos and then unpause and check it out. Right, so I've got methanol plus water. It's going to make CO2 and H plus, and that's exactly what it told me where I've underlined in pink. So all I've got to do now is make sure the elements are all balanced. I can see straight away I've got one hydrogen and I've got two over here, but I've also got three there. Okay, so I've got six hydrogen on the left and only one over here. So straight away we need to whack in a six. Now I've got six hydrogens on the right and I've got six hydrogen atoms on the left. Let's check out the oxygen. I've got one here in the methanol, one here in the water, and I've got two here in the carbon dioxide. So oxygen's fine. And I've got one carbon in the carbon dioxide and one in the methanol. So the carbon and oxygen, perfectly fine. We just needed to add in those hydrogen ions. Now check the electrical balance. It's neutral on the left, on the reactant side. It's not neutral on the right. So let's whack in our six electrons. Neutralize. Okay, what is this? Oxidation or reduction? Well, little clue, it's happening at the negative electrode. Hmm. Uh, and does that help? I don't know, but the equation helps. You've got electrons coming off on the reactant side. So this is oxidation. So we've got oxidation going on here and electrons being lost. So beautiful. Right, what do we need to do? Why is that important? It's important for my next step. So 8.3, the standard electrode potential for the carbon dioxide. Let's get me a little highlighter red thing out. Here it is. Eight. Yeah. All right. Enough said. 8.3. The standard electrode potential for the CO2 to methanol electrode is plus 0.03 volts. Calculate the standard electrode potential for the oxygen H2O electrode. So we've got one of the electrodes, we've got the other electrode. Well, we can't know that unless we have another bit of data. Like in all equations, you kind of need 2 out of 3 to work out the third. Guess what? Roll back up to the top here. We've got the overall reaction. Bear in mind, this is the overall reaction. We have a little, and that is plus 1.2. So we've got a little thing that's going to help us here. One sec, scroll that down. Bear with me, people. Right, this is what you need to be doing. EMF, okay, is equal to the standard electrode potential of the reduction equation minus the oxidation equation. Okay, redox goes in the perfect order, doesn't it? So it goes in the order when you say redox reaction. So we take the reduction half equation, the electrode potential for it, and we minus it from the electrode potential for the oxidation half equation. And that will give us the overall equation. But in this version, we've been given the EMF of the overall. Look, been given this up above. It was 1.20 volts. So that's not what they're asking us to find. They're asking us to find one of these. Well, they're asking us to find, actually, they've given us the electrode potential for this up here. They've told us that this is equal to 0.03 volts. Now, we just decided that that was oxidation, so we know that's 0.03. This one here, if we go back, this was the first half equation we wrote in the question, and that one had the addition of electrons on the left-hand side, so it was reduction. So that's the one we're looking for. So what's it going to be? Well, something minus 0.03 equals 1.2, and you got it. It has to be 1.23 volts, and that's your answer. So do remember that. That comes in handy. Your electromotive force is equal to the standard electrode potential for reduction minus the standard electrode potential for oxidation. Awesome. And that will get you a mark. Okay, let's have a little butchers at 8.4. State why a fuel cell does not need to be electrically recharged. So why don't we need to electrically recharge a fuel cell? Now, if your parents drive a Tesla or an electric car or whatever, they're going to have to recharge it, right? But if you've got a hydrogen or any type of fuel cell going on in there, then you won't have to recharge it. And why is that? That's because fuel cells, the fuel is in constant supply. They're constantly supplied with fuel. So continuous supply of fuel. Okay, or we could say reactants in constant supply. If you don't like to write the word continuous or continuously, you can just say constant supply of reactants. Okay, cool. One more mark. All right, I'm going to wipe this all out. So get down any notes you need. And we're going to go to the last part of the question. And it's just a nice, easy one marker. So 8.5 suggests one advantage of using methanol rather than hydrogen in a fuel cell for use in cars. Well, you might be baffed here, but it's a suggest. What do you know is a difference between hydrogen and methanol at room temperature and pressure? You should know methanol is a liquid. It's much easier to store liquids. So methanol is a liquid. It is easier to transport, and store. I mean, also being a liquid, you can fit more in. It's a lot more dense than a gas. So if you store a gas, you won't actually have as much energy per volume, like per centimeter cubed or per gram per mass either. So if you're storing loads of hydrogen gas as a gas in a car, you're not going to be able to store as much as you could in liquid form. Of course, you can't store as much as you could in solid form, but it'd be a little bit difficult to use a solid in a fuel cell. Okay, super duper duper. Hope that helps, guys. Make sure you subscribe, share, like, share with other students. Don't be a hater, be a lover. Share with other students on your course, and let's get to the marks. Oh, for chemistry, let's get into the question. It's question 9. This is a question about TOF, or time of flight mass spectrometry. Give the equation including state symbols for the formation of Sr plus ions from Sr atoms by electron impact. Okay, so looking at strontium here, and we're looking at electron impact. That means when the electrons smash into the atom and knock off other electrons, making it an ion. So a couple of things here. We want to show the atom in its atomic form, so no charge, being hit by an electron. We use the E minus symbol, and then we do the arrow showing it as an ion. An electron has been knocked off. Now, if an electron has been knocked off, it joins with the electron that hit it to form 2 electrons. So you've got a stream of electrons banging into these atoms and removing an electrons, and those electrons join the stream. Now, we don't forget the gaseous state symbols. So whenever you're doing mass spectrometry, the symbols are gaseous. And that doesn't matter whether it's electron impact or any other form of ionization. Electrospray would also be gaseous. Okay, let's check out 9.2. A sample of strontium is analyzed by TOF mass spectrometry. The sample is ionized by electron impact. The ions are accelerated to have a kinetic energy of 7.02 times 10 to the minus 20 joules. An ion takes 9.47 times 10 to the minus 4 seconds to travel along a 95 centimeter flight tube. That's going to be 0.95 meters. So we just make our immediate conversion there, because distance in equations is normally in meters. Kinetic energy is half times mass velocity squared, and that's where mass is in kilograms and velocity is in meters per second. Now we're going to need the speed calculation. Normally for these time of flight calculations, you'll need the speed equals distance over time as well. So once again, mass is going to be in kilograms, so that's going to be important. You'll probably need a conversion there, and speed is in meters per second. And that just reminds us the fact the speed is in meters per second, that we need to convert that distance from centimeters to meters. So if you're wondering why I converted that, that's the reason. We're going to need Avogadro's constant, and the actual calculation or the problem we're being set is to deduce the mass of one ion. No, not deduce the mass of an ion. That's important, actually. It's not to deduce the mass of an ion. That'd be a very small number. This is to deduce the AR, or the mass number of this ion. So there's a mistake we could have made there. And that's important because if it was electrospray, we'd need to add -1 from our final answer, but we don't here because it's electron impact. So we haven't added a proton and increased its mass. Okay, let's have a little butchers here. What we're going to do is distance, which is 0.95 meters over the time, which we're told up here, underlined in pink, is 9.47 times 10 to the minus 4. And that's going to give us the speed Okay, so that's going to give us the speed of the ions traveling along the tube, along the 1 meter tube. And so we write our speed out here, and that's in meters per second. And speed is interchangeable with velocity in this. I know velocity is a vector quantity and all that business, but essentially it's interchangeable with speed. So we're going to take our speed or velocity across, and we're going to whack it into the k equals half times mv squared equation. Now we want to get rid of the half m, so we times both sides by 2, which gives us 2 times the kinetic energy. And then we want to isolate the m on its own, so we're going to divide that by the velocity squared, which we've got here, and that's going to give us our mass, which is what we're going to need if we're going to work out the mass number. So what do we need to do here? We need to do 2 times the kinetic energy, and we've been given that above. I've underlined it in pink. It's the first thing underlined in pink. 7.02 times 10 to the minus 20 joules. So we're going to go 2 times 7.02 times 10 to the minus 20 joules. Oh my gosh, it's early in the morning. And then we're going to divide that by the velocity squared. Velocity is the same as our speed here, so we're going to divide that by 0.03.167899, which we're going to square. Don't forget to bracket everything in these equations, otherwise it comes out wrong. So oh gosh, I'm using a combination of handwritten and type. That's never a good thing. But don't forget to bracket everything in your calculator. And you don't really have to type out all these long, dirty numbers, because you can just keep it straight into your scientific calculator. You just need to make sure you're writing the working out as you go in case you make a mistake. So just make sure you're writing the working out, keep the scientific calculator on the side, you're keeping the numbers in it all the way till the answer. Okay, now my answer that I've got is 3.95. You might get 3.96 depending on what you've put in, times 10 to the minus 25. Now that's the mass, and that's going to be in kilograms. And they reminded that, I've underlined it in pink over there, where m equals mass in kilograms. Okay, but we are looking at the AR, or the mass number of this ion. And in the periodic table, what is the mass number? It's the mass in grams of 1 mole of a substance. So we're looking at the AR in grams here. Okay, so we're looking at the mass of an ion or atom when you have 1 mole. So I need to times by 1,000 to get it into grams. So I'm going to do 1.395 times 10 to the minus 25 times 1,000, and that's going to give me 1.395 times 10 to the minus 22. That's 1.395. I've written 2, but I can't bother to cross it out. So there we go. Make sure you put a 3 there. And then that's going to pick you up some marks, lovely marks all over the place here. What do we need to do next? Well, we've got the mass of 1 ion, but we need the mass of a mole of ions. Guess what? We've been given Avogadro's constant that you can call L. And that's 6.022 times 10 to the 23. So we want to, if we want to find out the mass of 1 mole of these ions, which is the mass number, we're going to times it by 6.022 times 10 to the 23. And that's going to give us a whole mole of the ions, which is going to be equivalent to the mass number. And if we pop that in the calculator, I think, oh, I've got 83.987 on my calculation. Now, it doesn't say, but you'd normally round this to 1 decimal place. So 83.987, well, let's round that actually up to 84, because our mass numbers are generally going to be whole numbers. And so we'll round that up to 84 to calculate the mass number of that ion. Super, I've circled it here. All right, nice one. Let's move on.
Keep moving on, keep moving on, keep moving on, keep moving.
So what have we got here? We've got 9.3. Explain how ions are detected in the TOF, time of flight, mass spectrometer. State how the relative abundance of the ions is determined, how the ions are detected, how the relative abundance is determined. Okay, so first of all, how are the ions detected? Well, after electron impact or electrospray ionization, they're going to be positive, these ions. Now, as they move towards the detector plate has electrons running through it. And those electrons are negative. So as the ions get close, those electrons are going to be attracted, and they're going to zap out of the plate towards the positive ion, forming a current when it gets close enough. So if you connect an ammeter to the detector plate, you'll get a reading on your ammeter to show that ions are arriving. Now, how do we know what the abundance, how much of the ions have arrived? Well, we look at the size of the current, and that gives you basically the size of the current is equivalent to the abundance of the particular ion. So if one particular ion arrives and you get 2 amps, and then another ion arrives, you get 4 amps, you know the second ion, there was double the abundance because it generated double the movement of electrons or double the current. Coolio. 9.4. So let's make a little space for 9.4 and scroll down. We have, let's get this in properly. Just adjust a little bit so I've got all the space for the working out. A sample of strontium contains 3 isotopes, SR86, SR87, and SR88. So 3 different isotopes. 82% of the sample is strontium-88. The other 2 isotopes are in a 1:2 ratio of 86 to 87. Calculate the percentage abundance of strontium-87 in this sample. It's going to get us 1 mark. Use your answer to deduce the relative atomic mass, the AR, of the sample. Give your answer to 1 decimal place. So there's another 2 marks there. So first of all, strontium-88 has 82%, but we've also got strontium-87 and 86. So we know if strontium-88 is 82%, then we know that 87 and 86 must be equal to 100 minus 82. Basically, they've got to make up the other 18%, right? If we add strontium-86 and 87 together, they've got to equal 18%. But we know they're in a 1:2 ratio. So let's divide 18 by 3. You get 6, and divide that up into 1 and 2. So you get 6 and 12. So strontium-86 is 6%, and strontium-87 is 12%. So you've got your first mark here because you've worked out the abundance of strontium-87, which is 12%. So we've just scored that first mark. Let's go to the next bit. Deduce the relative atomic mass, the AR, of the sample and give your answer to 1 decimal place. They're obviously the other 2 marks. So working out the AR and then rounding it to 1 decimal place is going to be the 3rd mark. So what we're going to do here is just what you do for any normal AR. You're going to do the abundance times the mass number of each isotope, add that all together to get the sum, divide it by 100, and voila. So 88 times 82 plus 87 times 12 plus we want 86 times 6. Or let me just write our abundance is 12% there for 87 in the right place. There we go. Well, that was the first mark we needed. So now we're going to do 86, just squeezing it in here around these 3 marks, times 6, and we want to divide that all by 100. That is going to give us our final answer of 87.76. And then we round that down here, as it says, round to 1 decimal place. You'll lose a mark if you don't, and you get 87.8. So you're going to get 1 mark for working out the abundance is 12% of strontium-87, 1 mark for the 87.76, carrying out the AR calculation, and then 1 mark for rounding to 87.8. Beautiful. 3 marks. Let's move on to the final part of this question. Let's go. Okay, so this last question to this, 9.5, electrospray ionization is used instead of electron impact for the ionization of a protein in a mass spectrometry experiment. Suggest why. So these suggest ones can always be quite difficult for some people, but think about it. Electrospray ionization is used instead of impact. What's the general difference here? When you use electrospray ionization, you add a proton in order to create the positive charge, so it will be attracted at the detector plate. With electron impact, you smash off an electron using a beam of electrons. The problem with electron impact, if you're doing a protein, what's a protein made of? It's made of amino acids. So I'm doing a real crusty G-level GCSE art, gangster level GCSE art drawing here. This is my protein, and it's being snapped here by the beam of electrons into fragments. Now, if you're trying to analyze the protein and work out its mass number, you might not want it to be fragmented. You might want to keep your protein whole and not be broken into pieces. So electrospray ionization would not be the best method. Sorry, electrospray ionization would be the best method because it avoids fragmentation of the protein, avoids it being snapped or broken into small pieces, whereas electron impact will do that. Okay, awesome. That's the final mark for this question. So, hope you enjoyed. Hit the like, subscribe, share. Yeah. So, this is from the 2023 paper one for AQA A-level chemistry. Question 10. This question's about weak acids. 10.1. Table 5 shows the pH ranges of some indicators. Hopefully you remember what an indicator is. It's a chemical that changes color when it changes pH. So bromocresol green has a pH range of 3.8 to 5.4. That means it changes color within that pH. Bromothymol blue 6 to 7.6 and thymol blue 8 to 9.6. Identify the indicator that would be most suitable for a titration between propanoic acid and sodium hydroxide. Pause the video, have a go. Now, hopefully you will remember that propanoic acid, an organic acid, a carboxylic acid, that means it's a weak acid, partially dissociates in solution. And sodium hydroxide, it's not a string, it's a strong base. Okay. And so we want to find the endpoint, or the equivalence point needs to be between a weak acid and strong base, not, we don't want our pH range for our indicator to be either in the pH of a weak acid or a strong base. So a weak acid is what, 3, maybe 4 to 6. So we don't want an indicator that changes color between 4 and 6 because it will change color if I have the weak acid in the conical flask. We don't want an indicator that changes color between like 12 or 13 to 14 because that will change color if I have my strong base in the conical flask before we've even done the titration. So which ones are out of the question here? We can't do 3.8 to 5.4. So bromocresol, no good with weak acids. Bromothymol blue, not really good with weak acids because it can change color at pH 6. So if your weak acid is there, it's going to change color already. So the only usable one is thymol blue, which will not change color if you have the weak acid or the strong base in the conical flask added with the indicator. Okay, cool. So thymol blue is your answer there. Right, let's go down to 10.2. Give the expression for the acid dissociation constant Ka for propanoic acid CH3, CH2, COOH. Now, we want the dissociation constant. We want the expression for it. So you should remember with Kc or Ka, you're looking at products over reactants, the concentration of the products over the concentration of the reactants. What we have to think about when we're dealing with the dissociation of a weak acid like propanoic acid is, what are the products? Well, propanoic acid would be the reactant, so that's CH3, CH2, COOH. What would it break down into? You should remember that propanoic acid will break down into propanoate ions, which is CH3, CH2, COO with a minus sign because it's a negative ion. And those hydrogen ions will come off. That's why it's an acid. It releases hydrogen ions when it dissociates. And so those will be the reactants. So we want to put the reactants over the products. And here's the equation for that. We use a reversible symbol because it's a weak acid. Strong acids, we wouldn't use this reversible symbol. And it forms the propanoate ions or carboxylate ions and hydrogen ions. Now, one thing I've got to add to my expression is I need to show that I'm dealing with concentration and I'm not dealing with moles or something else. And the way to show that, do you know how to show concentration in an expression like the Ka expression? You should add, and you probably know this, you've got to add square brackets. Now, you must make sure they're squared off. And I know you might think, does it really matter? It does matter. If you use curved brackets are used for pressure. Square brackets like this are used for concentration. So we have the concentration of our reactants here over the products. Apologies if you can hear the sound of my daughter running around and screaming in the background and shouting, asking me for another frube. Can I have a strawberry frube? Blah, blah, blah. There we go. Right, so yeah, little note, make sure you use square brackets for concentration, rounded brackets for pressure. Okay, we're going to move on to 10.3. Calculate the pH of a 0.1 mole per decimeter propanoic acid solution. Give your answer to 2 decimal places for propanoic acid where the pKa is 4.87. Okay, so just highlight here, this is the expression we're using. We want to find H+. If you want pH, you've got to do the minus log H+, so, or the hydrogen ion concentration. That's what the pH is. So what we're really doing here, we want to rearrange this equation that we had in 10.2 to make hydrogen ions the subject of the equation. So how are you going to do that? Well, we can start by saying hydrogen ion squared at the top. We can rewrite the expression with hydrogen ion squared because we know that the concentration of the H plus is equal to the concentration of the carboxylate ion. So we can just make that H plus squared. So then we can rearrange this by doing Ka times the concentration of the acid square rooted. And that will give us the hydrogen ion concentration. Now, we need to find Ka because they've given us pKa, which is really cool. Like if you want to plot Ka on a graph, it's really unwieldy because it's often times 10 to the minus 7 or something like that. So pKa gives you nice numbers for plotting in graphs. So we often convert Ka, the acid dissociation constant, to pKa. Well, we need to convert pKa back to Ka to put in this expression. And what you do there is you go shift minus log pKa, and that gives you the Ka. So press shift on your calculator, minus log, and then put in 4.87, and you're going to get 1.3489 or 1.35 times 10 to the minus 5. Now that's the Ka, so we want to times that by 0.1, which is the concentration of our acid circled here. And then we want to square root the answer. And if we do that, we get 1.16 times 10 to the minus 3 mole per decimeter. And that's our hydrogen ion concentration. But we're not done yet. This will have secured us 3 marks. So rearranging the expression and then finding the Ka from the pKa will get you 2 marks. Now we've got the hydrogen ion concentration. Hopefully you can remember how to work out the pH from the hydrogen ion concentration. And pH is the minus log of the hydrogen ion concentration. So get your calculator out, press minus, then press the log button, and then put in 1.16 times 10 to the minus 3, press the equal sign, and you're going to get the pH. Now, for the 4th mark, so this will get us our 3rd mark, working out the pH here, he says, although, yeah, zing this in my calculator, guys. And we get the number 2.93616, and that's the pH of this propanoic acid solution. However, don't forget that this question asks for us to do this to 2dp. That means 2 decimal places. And always forget these things. That's why you must use a highlighter or circle or underline the stem of the question. So we're going to round that up to 2.94 because the 6 is bigger than the 3. So instead of 2.936, it goes to 2.94, 2dp. Awesome. That's the end of the question. Let's get on to the next part, 10.4. Okay, so for 10.4, here we go. This is more of a kind of buffers, similar to a buffers question, because you're dealing with a weak acid and the salt of the acid. So for butanoic acid, the Ka is 1.15 times 10 to the minus 5 mole per decimeter. We've got 20 centimeters of 0.1 mole per decimeter sodium hydroxide solution. That's added to 25 centimeters of 0.1 mole per decimeter butanoic acid solution. Calculate the pH of the solution form. First of all, we need to look at the reaction. Sodium hydroxide with a carboxylic acid with one hydrogen ion to give away is going to be a 1-to-1 reaction. So now we're going to work out the moles of sodium hydroxide and the moles of butanoic acid. And you can do that with the N over CV. And this is going to get you 2 out of 5 marks, even if you can't do the rest of the question. So just stick to the basics. You've seen volume, you've seen concentration, so N over CV. So we're going to do 0.02. Remember, you have to divide centimeter cubed by 1,000 in these questions. So we've got 0.02 times 0.1, and that gives us 2 times 10 to the minus 3 moles of sodium hydroxide. Now, for butanoic acid, we've got 0.025 for the volume, decimeters, times 0.1 is going to give us 2.5 times 10 to the minus 3, and that is the moles of the carboxylic acid. Now, when the acid and alkali neutralize together, we're going to have an excess of one of them because they're not quite 1-to-1. It's a 1-to-1 ratio, but the amounts we have are not 1-to-1. So we're going to take the bigger amount, which is the acid, 2.5 times 10 to the minus 3. We're going to subtract 2 times 10 to the minus 3 for the sodium hydroxide. We're going to be left with 5 times 10 to the minus 4 moles of acid left over. Why is this important? This will have secured you 3 out of 5 marks, which is pretty cool, right? So you've worked out the excess acid. And this is because we're going to use the buffer equation. And for the buffer equation, when you're working out the pH of a buffer, you're going to do the hydrogen ion concentration is equal to the Ka times the acid over the salt. Now note, when you've got a strong alkali or base like sodium hydroxide, it's going to fully dissociate just like a strong acid. So that is going to fully, and in this equation actually, the sodium hydroxide is fully reactive because we had excess acid. It's all been used up. So we know exactly how much salt we've got we know that we've got, what was it, propanoic acid, butanoic acid. So we know we've got like 0.2 moles, 2 times 10 to the minus 3 moles of sodium butanoate, which is the salt. So we're going to do the amount of acid left over, which is 5 times 10 to the minus 4, divided by the concentration of the salt, which is equal to the concentration of the base. Okay, so, and then we're going to times that by the Ka. So 1.15 times 10 to the minus 5 times the acid, which is our excess left over, multiplied by the salt. Remember, there's no base left here. You're not doing acid divided by base. You're doing acid over salt. Just so happens that the salt is equal in moles to the base. Now, we could, if we want, turn this into concentration by dividing by the volume, and we're told that we've got 20 and 45 centimeters, so we've got 0.045 decimeters. So I could divide all these moles by that, but they're going to cancel out, and it's a ratio, so I can just use the molar ratio, and we're going to work that out as 3.775 times 10 to the minus 6. That's the hydrogen ion concentration, and you'll get the exact same answer even if you convert the moles of the acid and moles of the salt into volumes. You'll get the into concentrations, you'll get the exact same. And when we minus log that in our calculator, press minus, press the log button, the bracket will come up, put in the 3.775 times 10 to the minus 6, and you'll get 5.42 as the pH. And that is the answer for 5 beautiful marks. All right, guys, we're moving on to the very last part of the question. So let's zing. Here we go. 10.5. A student plans to titrate butanoic acid solution with a solution of ethylamine. Explain why this titration cannot be done using an indicator. So pause the video, have a go. Okay, you should spot butanoic acid, carboxylic acid. It's a weak acid, partially dissociates. Ethylamine, weak base. What's the issue? Well, our weak acid's going to be like pH 3 to pH 6. Our weak base is going to be pH like 8 to 11 or 12. And this means we're not really going to get a really straight vertical section at the end point when we carry out the neutralization. We're going to get a gradual change because of this, and therefore there'll be no suitable indicator for that. So the 2 marks, one for saying spotting that you're dealing with a weak acid and a weak base, and the next one for spotting that you won't get a straight line at the end point, you're going to get a gradual curve. And there we go.
You still
Let's get to
here?
the marks.
It's over.